As I have said when I talked about conditional probability and independence, if we look at the probability of E intersection with F, we said that this is the probability of E given F. That's the probability of F. At the same time, you can also, since again intersection is symmetric, this is the probability of F given E times the probability of E. So if I take these two sides of this equality, I'm saying that the probability of E given F is the probability of F given E times the probability of E divided by the probability of F. Okay? This is a very important result in all of statistics. This is known as Bayes' rule or Bayes' theorem. Okay? Bayes' rule or Bayes' theorem. Okay? And Bayes' theorem is the foundation for a whole field of statistics that's known as Bayesian statistics. Okay? Now, while I'm talking here about any two events P of E and F, and again here keep in mind that we want P of F not to be zero, of course. The more interesting or the more general application that we usually look at in terms of Bayes' theorem is in terms of what we call the law of total probability. Okay, so I want to actually take it a little bit beyond these two events, and there is something known as the law of total probability. Okay, and what is the law of total probability? Suppose that we have a sample space S, and suppose that we have sets B1, B2 all the way to Bn form a partition of S. I remind you what a partition is. Each one of these B's, B1, B2 all the way to Bn, is non-empty. Any two of them are disjoint. So if you take any two of these sets here, their intersection is empty. If you take the union of all of these, it gives you the sample space S. Okay? So a partition satisfies these three properties, that none of these sets is empty. The intersection of any two of them is empty because they are disjoint, and the union of all of them gives us S. The law of total probability tells us that if you take A to be an event, so you take A to be an event, the law of total probability tells us that the probability of A is the sum from I equal 1 to n of the joint probability of A with each one of these BIs. Okay? In other words, I can write it as from I equal 1 to the probability of A given BI, the probability of BI. Okay? So this is what the law of total probability is. A very important special case of this law is when we talk about two events. For example, if we talk about or a partition of the sample space into two events here. So if I look at the partition being or two events A and B, for example, here, and I can now talk about the probability of B given A being the probability of A given B times the probability of B divided by the probability of A given B, the probability of B, plus the probability of A given B bar times the probability of B bar. Now, where did this come from? Remember that this whole thing here, because B and B bar form a partition, they are a partition of S. this whole thing equals P of A, right? And remember that P of B given A is P of A given B times P of B divided by P of A. So this whole thing there in the denominator is the probability of A, but using the law of total probability, we conditioned it on the elements of this partition, a specific partition which is B and B bar. So we are interested here in just two events. We are talking about events A and B, and when we look at A in the denominator, we are talking about the joint probability of that A with B and with B bar. And B bar, remember, if you think about B and B bar, they are disjoint, of course, and if you take their union, it gives you S back. So it is a partition. P and B bar is a partition, and we can look at P of A as P of A B plus P of A with B bar. And this is what allows us to do this. So if I want to write it a bit, just write it again more cleanly here. So if I look at P of B given A, it is P of A given B, P of B divided by the probability of, actually, sorry, the probability of A given B times the probability of B, and this will be here the probability of A in the denominator, which is the probability of A given B, probability of B plus the probability of A given B bar, probability of B bar. This is the most standard form of Bayes theorem, okay? Bayes theorem. And it looks like a simple theorem that just follows from the law of total probability, which is really what all there is to it. But the uses of Bayes theorem are very, very powerful, and I would like to illustrate now one such case, one example that so many of us have experienced or have dealt with, which is the case of one shows up to a hospital or to a clinic and does a test. Imagine it's a test for some sort of, a terrible disease, and the test comes back positive. Okay, so the test comes back that, you have the disease. Now, when the test comes back positive, the question is, does that mean that one has the disease or no, right? So usually these tests are not perfect. And when the test comes back negative, it doesn't mean the person doesn't have the disease. They might have the disease with a certain probability. And if the test comes back positive, it does not mean they necessarily have the disease. They could maybe be healthy, not have the disease with a certain probability as well. So usually really one of the big questions that we are interested in is that if a test comes back positive, what is the probability? What is the probability that the person has the disease? Okay. So imagine I go for a test and they say, we did the test X and you have the disease. Of course, I am, to have hope, I would say, is there a chance that the test is wrong? And this is really what this question is about. Yes, the test came back positive, and we now are in the era of the coronavirus and COVID-19. And I'm sure some of you have heard in the news that the tests that they are running are not perfect. These tests could have one of two types of errors. That one of them, we call it false negatives. False negative, if n. And one other type of error we call false positive, if p. Okay, false negative is when the test is negative. the test comes back negative, but the person has the disease. Okay. False positive is when the test comes back positive, test is positive, but the person doesn't have the disease. Okay. And both of them are not great, because if the test comes back negative and the person does have the disease, it's a problem, because the test came back negative. Maybe one will say, okay, no need for treatment for this patient, but the patient does have the disease. The test is just wrong, and that's not a good outcome. Also, the case of false positive is not great, because if the test comes back positive, you might start administering treatment to that patient, even though that patient did not actually have the disease. And this does happen. So, for example, in the case of cancer, it's been documented many times that some people underwent chemotherapy, even though after the fact, it was discovered that the person did not have cancer. So, false positive might sound like a better outcome than false negative, because what can go wrong? We assume the person has a disease and it turns out they don't, but in practice there could be very bad implications to that. Again, as I said, in the case of cancer, a test coming back positive by mistake, and one administers chemotherapy to a person who doesn't have cancer, that's not a good outcome. So really, when these tests come back, our interest is in asking, what is the probability that the person does not have the disease, even though the test said they do? Or asking, what is the probability that the person has the disease, even though the test said they don't? Okay, these two possibilities, we want to put a probability. Really, we want to put the probability. What's the probability of a false negative? And we want to put the probability on the false positive. Okay. So, for example, for a perfect test, this will be both 0. And I don't know of any such test. Okay. So, in the medical field, I have never heard of a test that's this perfect, that will never make a mistake in either of these two ways. Okay. So, the way we answer this question is using Bayes' theorem, and I will illustrate this with the following example here. Okay. So, suppose that we have the following scenario, that one person in every 100,000 have some, we don't need to name a disease, but suppose we are talking about a certain disease, and we say that here are some facts. One in every 100,000 people has a disease. Okay. So this is basically how common is this disease. So if we say 1 in every 100,000 people have the disease, we are saying that 1 in every 100,000 people have specific disease. So if cancer, for example, if this belongs to, if this refers to, let's say, lung cancer, we are saying of every 100,000 people in the United States or in the world, one of them has lung cancer. Okay. Now, another fact is that, suppose we have a test for this specific disease, and the test gives positive result. Test gives positive result. Positive result 99% of the time when given to someone with the disease. Okay, when given to someone with the disease. So this is the true positive here. If someone has the disease and you give them the test, 99% of the time is going to come back positive, which is good. Okay. But when given to someone without the disease, it will, in 99.5% of the time, it gives a negative result. Okay. So this is the true negatives here. So if the test gives negative result, in, let's say, 95% of the time, let's say, I changed the number slightly, of the time, when given to someone who doesn't have the disease. Okay, so again, there are three facts written here so far, that one of in every 100,000 people has the disease. This is how common the disease is. The test gives a true positive, which means that the test comes back positive on a person who has the disease 99% of the time. The test has a true negative 95% of the time, which means that if you give it to someone without a disease, it comes back negative in 95% of the time. What this means is that in 5% of the time, so from these two we can conclude, we can immediately draw that if you look at the first one here, the test gives positive results 99% of the time when given to someone with the disease. Basically this means that the test gives negative result in 1% of the time when given to someone with the disease. Okay, so this really is following from here. So what we are saying, that if you give the test to someone with the disease, 99% of the time it comes back positive, which means 1% of the time it comes back negative. Okay, and from the second bullet here is that if the test gives positive result in 5% of the time when given to someone without the disease. Okay, this again follows from here. Okay, so now the question is, what's the probability a person who tests positive has the disease? Okay, so how do we answer this? So we have to now define two events. What we can call them, since we have disease and test, let's call them T and D. Okay, so we have T is the event that the test is positive. Okay, and we have D that the person has disease. Okay, so D bar is the person doesn't have disease, and T bar, the test is negative. So now I'm asking, what's the probability that a person who tests positive has the disease? Okay, so if I translate this to the language of probability, I'm asking, what's the probability a person who tests positive, given that the person tested positive, what's the probability they have the disease? So I'm asking, what's the probability of having the disease given that they tested positive? Okay, so how do I compute this? What I don't have this in any of the bullets I wrote up. What we have there are the probability of T given D and so on. So Bayes' theorem allows us to compute this, because this is the probability of T given D times the probability of D divided by the probability of T given D times the probability of D plus the probability of T given D bar, probability of D bar. Okay, now let's look at them one by one. I don't need to write these values down, but let's look at them one by one. Let's take this here. What is this probability of T given D? What's the probability that the test is positive given that the person has disease? The probability the test is positive given that the person has disease is written already there. This is 99%. Okay, It's the first bullet on this slide here, or this screen. Okay, look at the first bullet there. Test gives positive results 99% of the time when given to someone with disease. So if someone has the disease, given that someone has the disease, the probability of testing positive is 99%. What's the probability that the person has a disease? The probability a person has a disease, again, it was written, if I go up a little bit here, it's 1 in every 100,000 has a disease. So the probability of having the disease is 1 in 100,000, okay? So now I go back to these. What's the P of T given D? This is still 0.99. P of D is still 1 over 100,000. Now, what's the probability of the test coming positive given that the person does not have the disease? The probability the test comes positive given that the person does not have the disease is this 5% that we wrote here. Okay, so this is the 5%, 0.05. What's the probability that the person doesn't have the disease? It's 1 minus 1 over 100,000. Okay, so this is 0.99999. Okay, and you just multiply all of these, you will get the probability that the person has a disease given that the test came back positive. Okay, and if we wanted to compute what's the probability, I'm not going to put numbers now, if we wanted to compute what's the probability that the person doesn't have the disease given that the test is negative, okay, this is the probability that the test is negative given that they have the disease times that they don't have the disease here, sorry, and times the probability they don't have the disease divided by the probability like this, and the probability of D bar given D, probability of D here, okay? And using this formula now we can quantify the probability of not having the disease given that the test came back negative, okay? These two, again, this is the first one here, what's the probability of D given T? This is the probability of a false positive, and the second one is the probability of a false negative. And Bayes' theorem is the right theorem, or the framework we use to reason about this. If you look in your textbook, it also has some nice examples about how to evaluate the probability that an email you receive is spam. And spam filter is one of the simple ways of thinking about a spam filter, actually uses Bayes' theorem to evaluate the probability that an email you receive is spam, okay? So just to reiterate here, or to summarize, is that if we look at Bayes' theorem, as I wrote it there, is that the probability of F given E is the probability of E given F times the probability of F divided by the probability of E, which is we can condition it now on a partition of the sample space, which is the probability of E given F, probability of F, plus the probability of E given F bar, probability of F bar. But I remind you again that if we have, you know, F1, F2, all the way to Fn is a partition of the sample space, then we can make this more general, and you can do for any of these F's here, Fi on E, it's the probability of E given this specific Fi times the probability of the specific Fi divided by, now we need to look at the sum from 1 to n, the probability of E given Fi, probability of Fi, okay? So this is the most general form of Bayes' theorem. It does, now this applies to more than 2 events, to any set of n events, such that those n events are a partition of the space. I want to end with just one very general word about Bayes' theorem, and especially that it relates these days to the notion or to machine learning in general. We have been talking about P of F given E and so on, but let's actually now replace F and E by two events that have better meaning. Suppose I'm talking about a model M and data D. Okay, so let's say the model is a fair die that I'm tossing once, or rolling once, and the data is one of the numbers between 1 and 6. Or imagine the data being the results from a tosses of a coin, and the model is, is the coin fair, is the coin biased, and so on. And machine learning, so much of machine learning is about actually inferring the model from the data. Okay, so this is given, and this is what we are interested in. Okay, so in machine learning you are given data, so you're given billions of pictures, and you want to learn a model that basically tells us whether pictures are cats or dogs and so on. The data could be English text, and the model can basically say something about, is this text coming from fake news or not, or the data could be DNA sequences, and the model can basically tell us about something about which species it came from and so on. Okay, Bayes' theorem tells us that if you want to evaluate the model, get the model from the data, is that you can actually find the model that maximizes this probability of the model given the data. Okay, so if I ask what's the probability of the model given the data, then we can basically use Bayes' theorem and say this is the probability of the data given the model times the probability of the model divided by the probability of the data. Okay, and this is, basically Bayesian inference, what we call Bayesian inference of the model. And without getting into too much detail or elaboration, usually P of D is really a constant in this case, because it has nothing to do with a specific model. So what we end up saying is that probability of M given D is proportional to the probability of D given the model and the probability of the model here. Okay, so what is this here that these three terms that I wrote here have names, and very important names. This one here is called the posterior. This one here is called the likelihood. And this one here is called the prior. Okay, and the inference, we usually go this way, so we evaluate from the prior and likelihood and posterior. And the word I want to say here is that really this formulation that I just wrote here is a nice mathematical summary of what the scientific method is and how scientists work. So scientists usually have some sort of a hypothesis on the world. Okay, biologists have some hypothesis about what's the origin of the coronavirus, what animal it came from, and so on. Likely that's what's encoded in the prior. Okay, so now we are saying, okay, I put some sort of a prior probability on my hypothesis or my theory. The likelihood is the first place where you see D appearing. Okay, so now you see D. So now you see the data. You start collecting data. A scientist collects data. They start with the prior, start here. Okay, they start here with the prior. They add the data in terms of the likelihood. Then they update their hypothesis by computing the posterior. So any true scientist who follows the true scientific method usually comes with hypothesis in mind. But a scientist should be open-minded to what the data says. And this is why you hear all the time, let the data speak for itself, or let the data speak. And, or you hear a scientist saying, I'm data-driven. What that means is that, yes, one has a hypothesis in their mind about the world or about some phenomenon, but at the same time, you look at the data, what it supports, And then you update your belief using this, in some sense, using this equation, and you get your posterior beliefs. You had your prior belief. This is prior to seeing the data. Then you saw the data. You updated your belief, and you have now the posterior. And this is the scientific method, and this is anyone who calls themselves a scientist should be using this. There are people who have some prior belief on the world, and no matter what the data says, they stick with their belief. So they go from their prior belief to their posterior belief, ignoring the data. These are not scientists. They belong in some other fields, and they are not of our interest in discrete math or in sciences in general.